Okay, dear students, welcome to my YouTube channel, and this is lecture 5. And in this lecture, we can discuss the in previous lecture we have to calculate the magnetic susceptibility for paramagnetic materials. Here, also we can calculate the same parameter, that is magnetic susceptibility, that is the um, magnetic susceptibility chi for paramagnetic materials. Same topic, but by calculating this in this lecture by alternative method, that is magnetic susceptibility for paramagnetic solid substances. So this is the alternative method for calculating the magnetic susceptibility, that is chi, called as induced dipole momentous per unit volume. So I already telling you there are magnetic moment is present within the material, paramagnetic material, and when we apply external magnetic field, but these um, dipole moments, these dipoles are in random direction. When we apply magnetic field on a diamagnetic material, these magnetic dipoles tend to align themselves in the direction of magnetic field. So here, if there are, because here also we have to calculate the magnetic susceptibility, but dipole moments are only due to the supine here. So there are supines, that is supine up and supine down, that is in absence of B, when there is no magnetic field, in absence of B, supine ups and supine downs are equal. If they are equal, the net magnetization in this case will be equal to 0. So there is no magnetization, and that means the induced magnetic momentus will be 0 here, because there is no magnetization within the material when there is no external magnetic field acting on it. If we place this paramagnetic material in a magnetic field, so some dipoles will tend to align themselves in the direction of magnetic field, so there is net magnetization produced within the material. So in presence of B, supine up and down are not equal. So most of the dipoles tends to align themselves in the direction of external magnetic field B. So there is net magnetization. So there is net magnetization induced due to the external field within the material, that is paramagnetic material. And here, if NAR and P, sorry, are magnetic dipoles parallel to be parallel to the magnetic field, and Na are the magnetic dipoles antiparallel to B. So there are maximum number of dipoles which are parallel to the magnetic field and can be denoted by Np, and Na are the number of antiparallel magnetic dipoles. So the net magnetization can be written as M will be equal to mu B Np, that is magnetic moment of one dipole multiplied by N, that will give us the dipole moment multiplied by the N number of dipoles, that will be the magnetization produced due to the N dipoles, Np dipoles, minus mu B Na. So mu B will be common and there remains Np minus Na. So this is the magnetization. Magnetization will be if there is Np greater than Na, when the number of dipoles parallel to the magnetic field in the direction of magnetic field greater than antiparallel. So there is net magnetization produced within the material. So mu B is also called as Bohr magnetron, which I have already discussed in lecture first. That is, its value will be H cross upon uh, H cross upon 4 pi m, and this is called as Bohr magnetron. So here you have to calculate the Np minus Na. If we calculate this, we so Np, as per the in previous lecture I am already telling you, this is a thermodynamic system and thermodynamics laws will be applied here. So here, as per the law of equipartition of energy, as per the law of equipartition of energy, we can write this Na is proportional to E power minus Ea, that is the energy of antiparallel dipoles, upon kBt. Similarly, Np parallel dipoles will be proportional to E power minus Ep upon kBt. So here Na will in equality, it can be written as minus Ea upon kBt with some constant of proportionality, and Np similarly will be C E or minus Ep upon kBt. Here kB is the Boltzmann constant, A is the energy associated with antiparallel dipoles, Ep is the energy associated with parallel dipoles. So these are the equations for Na and Nb. So after that we know the torque acting upon a dipole when this magnetic material, when this paramagnetic material is placed inside in between in a magnetic field. So there is net magnetization because these dipoles experience torque in this magnetic field, and there is energy associated with these dipoles, and this energy is Ea and Ep. So calculating this energy, we can write here torque will be equal to mu m, torque will be equal to mu mb, that is here we can write it as mu m. B will be equal to mu naught H, and the energy associated with this will be equal to integral of pi by 2 to theta torque, that is mu m mu naught H sine of theta d theta. So we have to evaluate this integral. We can get E will be equal to minus times mu m mu naught sine H cos of theta, and will be minus, because sine of theta will be minus cos of theta, minus cos of 90 will be 0, there is only cos of theta. So this is the energy associated with each dipole. So here we can write it in terms of A, EA and EP and substitute it here. Therefore we can write Na will be equal to C e power minus minus will be, here it is minus, here it is also minus, minus will be plus mu m mu naught H cos of theta upon, here the case is like this. Here you see first E will be equal to minus mu m mu naught mu b mu naught H cos of theta. So we can, this equation will be E will be equal to minus mu m mu naught H cos of theta. So for parallel and anti-parallel dipoles, if theta will be equal to 0, that is parallel dipoles, that is parallel, this equation will be EP. So cos of 0 will be equal to 1, that is minus mu m mu naught H. Similarly, if theta will be equal to pi, that is anti-parallel, that equation becomes E A anti-parallel, cos of 180 will be minus, that will be equal to plus, that is mu m mu naught H. So the energy difference between these two, that is energy difference will be equal to EP EA minus EP. This will become, this is minus EA minus EP, this minus this, that means minus minus plus, that is twice mu m mu naught H, or we can write it as twice mu m mu naught H will be equal to mu naught H will be mu naught H will be equal to B. So this equation is like this, that is, if this is EP, EP will be equal to minus mu m mu naught H. Similarly, EA will be equal to mu naught mu m H. This is for parallel, these are parallel, anti-parallel and parallel. The energy difference between these two will be equal to twice mu naught mu m H. We can write also here, if mu m will be also equal to mu b, we can write it as twice mu b into b, because there is magnetic moment associated with the electron, also called as Bohr magnetron. So here in this case we can write this equation. If we divide these two equations, so Na upon Np will become C and C will cancel, there remains e power, minus will be common, ea minus ep upon kbt. So this can be written as na upon np will be equal to, if it is 1 plus, here also it can be write as 1 plus e power minus ea minus ep will be equal to twice mu b into b upon kbt. So here we can put mu b upon kbt will be equal to some constant a. So here we can write it as 1 plus, here also 1 plus na upon np is approximately equal to n, that is total number of dipoles, upon np. So here in LHS we can write n upon np will be equal to 1 plus e power minus twice a. So here np will be equal to n upon 1 plus e power minus twice a. np will be equal to, if it is multiplied and divided by e power a, then it becomes e power a plus e power minus a. So this is np. Because we have to calculate the magnetization, that will depend us upon np minus na. So the value of np is this. Similarly, if we write here, if we write np upon na ratio, so this equation will be e power minus, that will become plus, here it is minus 2a, it will become twice a, and this is 1 plus, this will become 1 plus, and here n upon na will be equal to 1 plus e power 2a. Na will become n upon 1 divided by 1 plus e power 2a, and if we multiply e power minus a, this will become e power minus a plus e power a. So this is Na and this is Np. So their difference will give us the magnetization, that we can write magnetization will be equal to mu b into Np minus Na. So magnetization will be equal to mu b Np minus Na, that is this minus this, here n is common and there remains e power a minus e power minus a upon e power a plus e power minus a. So we can write m will be equal to mu b n. This function is equal to, that is the tan hyperbolic of a. So this is the magnetization produced within the paramagnetic material by applying external magnetic field. So this is magnetization. So here it is saturated, this is saturation magnetization. So if we here, if A is very large, if A is very large, because A depends upon, A will be equal to, we have to put already A, this will be equal to mu naught mu b upon kbt. So mu B Kb is constant here. Sorry, B is not constant, it is constant mu. So it depends upon value of B and T. If B is very large, T is very small, then A will be large. Then in saturation magnetization, here I am already telling you in previous lecture, here it is A in x-axis, here it is M upon Ms. In y-axis, the gap becomes this. The saturation is at large A, that is a saturation. So here we can write M will be equal to mu B n multiplied by tan hyperbolic A at this condition, because tan of A, if it is greater than 1, then tan of hyperbolic A will be equal to A, and it will be equal to angle. So here we can write it as A. So magnetization will become mu B n multiplied by value of A, that is mu B into B upon KBT. So this is magnetization. So this magnetization will be related to the susceptibility, that is M upon H. So this becomes mu B n multiplied, that is mu B square, mu B into mu B, that is mu B square, n into B, n into B. B can be written in terms of H, that is mu naught H upon KBT into this H. H and H will cancel, so there remains mu B square and mu naught upon KBT. So here you see mu B is constant, N is constant, mu naught is constant, so these are all constants. So chi only depends upon the temperature, that is there will be written single constant upon T. This constant is called as Curie constant, and this is the temperature. So the physical significance of this equation is same as I already tell you in previous lecture. Here if we increase the value of T, if we increase, that means we can increase the temperature of the specimen, this will reduce the magnetization, because the randomness of magnetic dipoles will occur at higher temperature. So higher magnetic field will be required, and at low temperature, so there is magnetization, maximum magnetization induced within the paramagnetic material, and this magnetization, this maximum limit is called as saturation magnetization. So here this law can be calculated by this alternative method. Thank you.